Welcome to this next video in the playlist on field theory. In this video what we're going to introduce is the concept of a separable polynomial. Okay, so we'll begin then with the definition of a separable polynomial, and then we'll explore which polynomials are actually separable polynomials later on. Okay, so the definition then of a separable polynomial. So this is a definition which applies to polynomials in a ring of polynomials over a field. Okay, so our starting point is that we're going to have some polynomial, f of x here, which is an element of the ring of polynomials over a field, capital F. Okay, and to apply the definition of separable to a polynomial, you need your polynomial to be a non-constant polynomial. So we're going to assume that this polynomial, little f of x here, is a non-constant polynomial. So that means that it's not the zero polynomial, and indeed it's not any of the other constant polynomials either. Okay, so it's degree 1 or greater. It's a non-constant polynomial. You can't apply this definition to a constant polynomial. Okay, so just to write this out explicitly then, so let's have f of x written out explicitly like so. f0 plus f1x plus all the way up to fn x to the n, where these fi's are the coefficients of the polynomial, so they're elements of the field, capital F. Okay, so we've got our polynomial here, and n is the degree of this polynomial, and what we know is that n is greater than or equal to 1, because we've assumed that it's a non-constant polynomial here. Okay, right, so what's the definition then of a separable polynomial? What does this polynomial have to satisfy in order to get this title of separable? Okay, well here it comes. So we have seen in the previous video on this playlist on field theory the concept of a splitting field for a polynomial over f. And we've seen firstly that it exists, and secondly that it's unique up to isomorphism, so we're entitled to talk about the splitting field for a polynomial over a field, capital F. Okay, so what I can now construct for any polynomial, my non-constant polynomial here, I can construct its splitting field over f, so do that. So let's construct the splitting field, and we will call it k, so it's going to be a field extension of f. And of course, if this polynomial completely splits already over the field capital F, then k will be a very boring field extension of f. It will just be equal to f itself. But if it doesn't already split into a product of linear factors in the ring of polynomials over the field capital F, then k will be more interesting. It will be a more interesting field extension of f. Okay, and remember the splitting field is the smallest field extension of f over which the polynomial splits completely into linear factors. Okay, so if you find a field extension of f over which the polynomial does split into linear factors, what you need to do to construct the splitting field is take all subfields of that splitting field, well, of that field extension of f, it's not a splitting field yet, which are field extensions of f and which contain all of the roots of the polynomial, and intersect all of those together, and then you'll end up with the smallest field extension of f, which truly contains all of the roots, and therefore is the splitting field for this polynomial, the smallest field extension of f which contains all the roots of the polynomial, and which therefore over which the polynomial splits into linear factors. Okay, so over this splitting field then, this polynomial will split into linear factors, so it will look something like this. So f of x, and this is a statement I can write only in the ring of polynomials over the splitting field, okay, is going to be equal to fn, the leading coefficient out the front, and then we'll have x minus alpha 1, where alpha 1 is a root to the polynomial that's in the splitting field, capital K, and then it'll be to the power of n1, where n1 is the multiplicity of this root, and then we'll go on, x minus alpha 2, here's another root, to the power of its multiplicity, n2, and then you'll continue on all the way down to x minus alpha k, where k is going to be less than or equal to n, and then it will be to the multiplicity of this root alpha k, which is nk here. Okay, so we can write our polynomial f of x in this way in the ring of polynomials over the field capital K, over the splitting field. Okay, so you can write this statement in the ring of polynomials over the splitting field capital K. Okay, so we haven't yet seen the definition of separable. This is all just talking about splitting fields. So what now is the definition of separable? Well, we call this polynomial f of x separable if, when you go into its splitting field and write it in this way in the ring of polynomials over the splitting field, all of the multiplicities are 1. All of the roots are simple roots, i.e. their multiplicities are 1. They only appear once. Okay, so all of the linear factors in this factorization into linear factors in the ring of polynomials over the splitting field are distinct. Okay, that's the definition of a separable polynomial. Okay, so if the polynomial was separable, then in the ring of polynomials over the splitting field, f of x will be writable like this. Fn times x minus alpha 1, and the multiplicity will be 1, times x minus alpha 2, and the multiplicity will again be 1, and you'll go all the way up to x minus alpha n. You'll have to have n distinct roots. Okay, and again the multiplicity of that will be equal to 1. Okay, so all of the roots must have multiplicity 1. All of the roots must be simple roots is another piece of nomenclature that we can use to describe this condition. So that's the condition for a polynomial over the field capital F to be separable over F. That when you construct its splitting field and then can write it as a factorization into linear factors in the ring of polynomials over that splitting field, that all of the roots are simple roots. They have multiplicity 1. All of the linear factors are distinct. Okay, and if that is indeed true, then we call the polynomial separable over the field capital F. So it's a separable polynomial over the field capital F. So separable over F. If it's not true, so if it's instead the case that when you take this polynomial and construct its splitting field, k, you get a factorization into linear factors and the roots are not all simple roots, so you do have some repeated roots, some roots where the multiplicity is greater than 1, then you call the polynomial inseparable. So polynomials are either separable or inseparable. Okay, so that then is the definition of a separable polynomial over the field capital F. So the first thing that I want to show you is that it's well defined. Okay, it has only one answer. So if I gave someone a polynomial from my ring of polynomials over the field capital F, and then I gave another person the same polynomial and I said, both of you go forth and decide whether this polynomial is separable or inseparable, they would come back with the same answer. That's what I mean by well defined. Okay, two different people doing this differently cannot come back and give me a different answer unless they've done something wrong. Okay, so why is it well defined? Well, the reason it's well defined is that the splitting field K is unique up to isomorphism. Okay, so when you are trying to work out whether a polynomial in the ring of polynomials over the field is separable or not, you have to construct this splitting field, and both of the people that I give the task to will construct the same splitting field. Okay, therefore they will get the same factorization into linear factors. Okay, and therefore they will come to the same conclusion that either it's separable and all of the roots are simple roots, or it's inseparable because not all of the roots are simple roots. Okay, so that's the reason that this is going to be well defined. Okay, now just before we do an example of this to get some feel for it, let me just add a little bit more into this concept that it's well defined. So I'm going to give you a claim here that's important as far as understanding is concerned. So the claim is that if you have any field extension of f, okay, so I'll write this out. So the claim is that let E be a field extension of f, okay? And let's say that E contains some roots for this polynomial f of x. Okay, so f of x has some roots. So remember, f of x is just our polynomial in the ring of polynomials over the field capital F. Okay, let's say that this polynomial is separable. Okay, so all of the roots in the splitting field are going to be simple roots. Then my claim is that if this field extension E of f has some roots for this polynomial, that they are still simple roots. Okay, so my claim is that if you have a field extension of f, and of course this polynomial is still perfectly plausible as a polynomial over this field extension, because this is a field extension of f, so all the coefficients are still in there. So it's perfectly plausible to view this as a polynomial in the ring of polynomials over E. Okay, my claim is that if you do indeed have roots for this polynomial in E, then they're still going to be simple roots. Okay, you're never going to be able to find some field extension of f where you have two roots for f of x if it's separable. Okay, and this of course is building on this concept that this truly is something that's ingrained into the structure of the polynomial. Okay, it's truly well defined to talk about a polynomial being separable or inseparable. It's a piece of information that's integral to the structure of the polynomial. Okay, you don't need, it's not a feature of the splitting field is what I'm trying to communicate here, or rather the splitting field is completely determined by the polynomial. All of the information in the splitting field is in the polynomial. Okay, so this information about whether it's separable or inseparable, it doesn't depend on this splitting field. It's completely dependent on the polynomial, because the splitting field which you use to decide is completely dependent on the polynomial. That's what I'm really trying to get across here. And this is taking this a little bit further by saying, okay, if you construct any field extension of f and you look for roots of this polynomial in that field extension of f, if it's separable, then you're always going to find that all of the roots have multiplicity 1 in here, i.e. they're simple roots. Okay, so let me just explain why this is, and hopefully that will give you more intuition as to why this is such a well-defined definition. Okay, so there are two cases here, so we'll split it into two cases. So the first case is that the field extension that we've generated of f is not actually a splitting field. Or rather, sorry, I don't want to call it a splitting field. It's not actually a field extension of f in which the polynomial completely splits, or rather over which the polynomial completely splits. I.e., if you look at this polynomial f of x in the ring of polynomials over E, it's not going to be possible to split it down into a product of linear factors. Okay, so you haven't got all the roots for the polynomial in here. The other case is where it is a field over which the polynomial completely splits, so it does contain all of the roots. Okay, but we'll start off with this case. Okay, so E is only going to contain a few roots of f of x. So what I want to now show you is that those roots must still be simple roots, i.e. when we factorize f of x in this ring of polynomials over this field extension E, we're not suddenly going to get a root appearing twice, i.e. it's not plausible for you to get something like this, x minus, let's say, alpha squared times f bar of x as your factorization in here. You cannot suddenly get this root appearing to multiplicity 2 over this field extension of E, okay, for this polynomial which I'm assuming is separable here. That's not possible to do. Okay, so I want to prove that this is not possible. Okay, the roots will all be simple in this field extension of f. So how can I do this? Well, what I can do, of course, is I can say, okay, let's build a field extension of E such that it's a splitting field for this polynomial over E. So what we can now construct is the splitting field k over E for this polynomial f of x. Okay, now this field extension of E, which is a splitting field for this polynomial, so over this field here, this polynomial will completely split down into linear factors. This is not necessarily the splitting field over f, so maybe I should call it k bar rather than k, so I don't confuse it with what I've called the splitting field for the polynomial over f. Okay, so the reason that this isn't necessarily the splitting field over f, so the reason that k bar isn't necessarily, so I'll put a question mark there, equal to k, is because we don't know how big E is. E could be a massive, massive field extension of f, okay, that contains all sorts of unnecessary things in it. And then when you build k bar, the splitting field over E, for this polynomial f of x, it's going to have to contain all of those unnecessary things that are in E. So because we don't really have that much control over E, and it could be a huge field extension of f containing all sorts of unnecessary things for as with regards to this polynomial splitting, then we don't know that this is actually the smallest field extension of f that you could build that would contain all of those roots for this polynomial. It's the smallest field extension of E that you can build, which would contain all of the roots to those polynomials, but that doesn't imply that it's the smallest field extension of f that would contain all the roots to those polynomials. However, the important thing is that this is going to be a field extension of f, okay, because it's a field extension of E. I can conclude that it's a field extension of f, and it is a field extension of f in which the polynomial splits completely, or rather over which, I should say over which rather than in which, over which the polynomial splits, because of course it's really splitting in the ring of polynomials over that field, not in that field. Okay, so this is a field extension of f over which the polynomial is going to split. So of course what I can then do is restrict it down to a splitting field for the polynomial over f by looking at all the field extensions of f that are subfields of it, which contain all of the roots to the polynomial. Okay, and if you intersect all of those subfields together, then of course you'll get another field extension of f which will still contain all of those roots, and that will now be the smallest field extension of f that contains all of those roots, and that will be a splitting field for f of x. It will still be the case that in that field extension of f the polynomial completely splits, because all you need is those roots in order to write your polynomial in this form, because fn is just from the field capital F, so that will certainly be there, and then all you need is all of these roots here, okay? Or rather, they're additive inverses, but of course if you've got the root, you've got its additive inverse as well. Okay, so you can use this to construct a splitting field, and the point is that all of the roots for the polynomial that were in k bar are still going to end up in k, and we know that k is unique up to isomorphism. So when you construct the splitting field from this by the method that I've just described, by intersecting all the subfields together, you will end up with something that's isomorphic to k. Okay, and of course you'll end up keeping these original roots that were in E, because these will be roots still in k bar, and then they'll remain in k. So if it was the case that you could find this field extension E of f, where you had this root appearing to multiplicity 2, this alpha to the power of 2 here, well, this alpha with multiplicity 2 here, that would remain in our splitting field that I was constructing in this way, okay, and therefore it would contradict the polynomial being separable. So, indeed, when you have this field extension of f, which has some roots for this separable polynomial, those roots must all be simple roots, okay, even if it's not a full splitting field of the polynomial over f. Okay, the other case, in fact we've really discussed it here, but I'll do it as a separate case anyway. The other case is that you have a field extension of f, which again I'll call E. So we have E, which is a field extension of f, and this time the polynomial does split over E. So in the ring of polynomials over this field extension E, the polynomial does split completely into linear factors already. Okay, the claim is then again that if the polynomial is separable over f, then all of these roots that we've got in this larger field extension of fe are going to be simple roots. Okay, and of course the reason there is that you can just restrict this down, and you can use this to build a splitting field. So just by the exact same way that we went to take k bar to the splitting field k, we can do the same thing with E here. So we can take all subfields of it that are field extensions of f, which completely contain all of the roots to the polynomial, okay, intersect them all together, and we'll end up with the splitting field for the polynomial over the field f, and it will be isomorphic to this one and only splitting field for the polynomial over the field capital F. Okay, but of course all the roots here will remain the roots here, and we know that all the roots here are distinct, they're simple roots, so here of course they also had to be simple roots. So both of these cases, whenever you've got some field extension of f, even if it's not a splitting field extension of f, the roots for this polynomial that is separable are still going to be simple if you've got them in that field extension of f. Okay, so that, I hope, furthers your understanding of how this definition of a separable polynomial is truly ingrained into the polynomial. All of the information is in the polynomial. Construct any field extension of the field f that contains roots to this separable polynomial, and all the roots are always going to be simple roots if the polynomial is separable. So it truly is a very nice, well-defined definition. Okay, so to finish this first video on separable polynomials then, let's do an example. Okay, so we'll do a concrete example. So we'll work with one of our favourite fields, which is the rational numbers. Okay, so we will take a polynomial then that's going to be in the ring of polynomials over the rationals. Okay, so what polynomial should I come up with? Well, I'm going to come up with the classical example that everyone uses to do simple examples in field theory. We're going to use x squared plus negative 2. Okay, that's certainly a polynomial that is in the ring of polynomials over the rationals. We've got the coefficient 1 in front of x squared, and we've got the constant term negative 2. They're both rationals. Okay, so that's absolutely fine. We've got a beautiful polynomial in the ring of polynomials over the rationals. Okay, so my question now is this polynomial separable in the ring of polynomials over the rationals? Well, of course, we know that it's an irreducible polynomial in the ring of polynomials over the rationals, okay, because we know that there are no roots to this, and this is a degree 2 polynomial, and if it was reducible, then there would have to be a root, because it would have to have a degree 1 factor, and whenever you have a degree 1 factor, you have a root. And because we know no rational squares to give 2, we know this has no roots. So we know it's irreducible, and that's going to actually help us in our argument for it being a separable polynomial. Okay, so how should we decide whether this polynomial is separable? Well, of course, what we have to do is construct a splitting field for this. We have to produce a field extension of the rationals where this splits. Now, as I've just said, it's an irreducible polynomial, so it certainly doesn't split over the rationals. So we are going to have to produce a proper field extension of the rationals. Now, of course, we could do this sort of in the synthetic way. I like to call it the synthetic way. We could view the rationals as a field, and that's all we know about, and then we could try and build something bigger, okay, in the way that we have indeed studied in the video on field extensions. But I think it's slightly easier to think about the rationals as being inside a much bigger field, and then just look for a field extension of the rationals that's a subfield of this much bigger field, which does indeed do the job of being a splitting field. And because we know the splitting field is unique, then we'll know that this is indeed isomorphic to any other splitting field that we could have constructed in the synthetic way. I think that's the easier way to approach this, but you could do it the synthetic way. Okay, so we know, of course, that the complex numbers is a massive great field extension of the rationals. Okay, a dream field extension of the rationals. Okay, a fantastic field extension of the rationals, and we're going to use this to find the splitting field, or something that, well, find the splitting field of this polynomial over the rationals. Okay, and of course, because, as I say, we know the splitting field is unique, if we find a splitting field, we know that that is the splitting field. Okay, right, so what I'm going to do then is look for a field extension of the rationals that's going to be a subfield of the complex numbers in which this polynomial is going to completely split. Okay, well, of course, I know that we have solutions to this polynomial in the complex numbers. We have roots to the polynomial in the complex numbers. Okay, so for instance, we have the square root of 2, which is a complex number. Okay, that's certainly an element of the complex numbers. So why don't we try generating the field extension of the rational numbers generated by the square root of 2? Why don't we try putting in a solution to this polynomial? Because we know that if we have a field extension with a solution in, then this is going to split down. Okay, so let's do this. Right, so let's try and generate this. Now, of course, the square root of 2 is going to be algebraic over the rationals, and indeed here is going to be its minimal polynomial. X squared plus the additive inverse of 2 here is going to be its minimal polynomial. We know this is an irreducible polynomial in the rationals. It's a monic polynomial in the ring of polynomials over the rationals, and indeed the square root of 2 does satisfy this polynomial in the complex numbers. Okay, so excellent. That means that to construct this field extension of the rational numbers, all we have to do is look at all polynomials with coefficients in the rationals evaluated at the square root of 2, which is something we can do in the complex numbers. Okay, so what we'll actually end up with is all things of this form: a0 plus a1 times the square root of 2, where a0 and a1 are elements of the rational numbers. And the reason is that when you go to polynomials with higher degree terms, so for instance x squared terms, when you put in the square root of 2 there, of course the square root of 2 will square in the complex numbers to give 2. Okay, so you don't actually get some new element, you get something that's already here. Okay, and indeed for all of the higher degree terms, there's no point to them basically, they just give you answers that you've already got. These are the only different answers that you can get in the complex numbers. So when you do indeed look at all polynomials over the rational numbers evaluated at the square root of 2, these are the only answers in the complex numbers that you can get, and we know from our study of field theory that this therefore is going to be the subfield of the complex numbers, that is the field extension of the rational numbers generated by the square root of 2. Okay, right, so this is going to be a field extension of the rational numbers, and indeed in this field extension of the rational numbers, this polynomial is now going to beautifully split, and indeed it can't split in anything smaller than this because you must have the square root of 2 in there for this to split. Okay, so this is the smallest field extension of the rational numbers that contains the square root of 2, therefore this must be the smallest field extension of the rational numbers in which the polynomial splits. Okay, so what we can now do is in this, or rather over this field extension, so in the ring of polynomials over this field extension of the rational numbers, what we can now do is write x squared plus negative 2 as x plus the square root of 2 times x plus the negative of the square root of 2, which of course are two elements that are certainly in there because you can put a1 is equal to plus 1 and negative 1, and a0 is equal to 0. Okay, and of course when you multiply these two out, you're going to get the polynomial x squared plus negative 2. Okay, so in this ring of polynomials over this field extension of the rational numbers, the polynomial does indeed split here. So this is going to be our splitting field for this polynomial over the rational numbers. And I want to stress that you could have done this the synthetic way. You could have tried to just view the rational numbers as a field in its own right and then try to build something bigger than it that contained roots for this polynomial. It's easier, in my opinion, to just view it as being contained in the complex numbers and acknowledge that this structure that we've built here is isomorphic to any other splitting field that you could have possibly constructed, so we might as well just use this nice thing that we've got beautiful symbols for already to actually represent our splitting field here. Okay, so this is the easiest way to do it, if you like. Okay, so this polynomial then is going to be separable because the two roots are distinct here. They've both got multiplicity 1, okay, they are both simple roots. So this polynomial is indeed separable over the rational numbers. Okay, and construct whatever field extension you like of the rational numbers. If it's got roots to this polynomial in, then they will always be simple roots. Okay, right, so we will have a break here, and in the next video what we will do is introduce an extremely helpful tool for understanding the separability of polynomials, namely the derivative of a polynomial.